Hey everyone, and welcome to this explainer. The deep sea is literally one of the most hostile frontiers on our entire planet. It's this relentless adversary that is actively trying to crush, freeze, and dissolve our multi-billion-dollar subsea production systems. When we're talking about plunging thousands of feet underwater, sure, the massive rigs up on the surface get all the glory, right? But down in the dark, math is our absolute only invisible shield.
And that brings us to the core problem we're tackling today. How exactly do you protect a pipeline that you can never, ever physically touch? We can't just guess our way out of subsea failure. We can't wait to see if a pipe bursts or freezes and then, just send someone down with a wrench. There's no way. We have to mathematically calculate our literal survival well before a single piece of steel even hits the water.
All right, so here is our roadmap for today. We're going to cover the 5 mathematical battles of the deep. That includes the mathematics of the deep, fighting sand and acid, the no-touch time clock, boosting declining production flow, and finally, surviving extreme ocean pressure. Let's dive in.
Section 1. Mathematics of the Deep. The Subsea Battleground.
Section 2. Fighting sand and acid. So let's talk about the Salama and Tulsa erosional velocity models. These models essentially set a hard flow ceiling for us. They calculate the absolute maximum speed our fluids can travel based on things like particle size, sand rate, fluid density, and geometry before entrained solids literally start destroying the pipe. Think of it kind of like water blasting a driveway. A gentle stream cleans the concrete just fine, right? But if you crank up the pressure and the volume, that stream actually starts stripping away the concrete itself. Well, sand-laden production fluid does the exact same thing to steel pipes, just over a slightly longer timescale.
Now, if we deconstruct these variables, we see that the risk is disproportionately concentrated at geometry changes. We're talking about places like elbows and T's where the fluid is physically forced to abruptly change direction, which slams those particles right into the wall. And here is an absolutely crucial rule to remember. Sand production rates almost always increase as a well matures. So an early life design that was perfectly safe, it can suddenly become an incredibly dangerous ticking time bomb at those elbows and T's a few years down the line if we aren't constantly adjusting our math.
Okay, shifting from physical attacks to chemical ones. The D-Ward CO2 corrosion equations are the industry standard for predicting just how fast carbon steel degrades. This corrosion rate is a highly sensitive function of 3 things: the partial pressure of CO2, temperature, and pH. When CO2 dissolves in produced water, it actually forms carbonic acid. It's exactly like leaving an open can of soda out on the kitchen counter. It slowly reacts with everything it touches over a matter of hours. In a subsea pipeline, that same slow, invisible chemical work is eating away at the solid steel over a matter of years. This is exactly why knowing your precise pH and temperature isn't just trivia, it is quite literally survival.
So, the critical point here is how you choose your defense against this acid. You generally have 2 options on the table. You can either pay a massive upfront capital cost for a metallurgical upgrade using a highly durable corrosion-resistant alloy, or you can rely on a chemical shield, which means continuously injecting a corrosion inhibitor to coat the inside of the steel. But catch this, chemical inhibitor programs fail completely silently. Even a very short, unnoticed gap in your chemical dosing allows for rapid, unseen wall loss. The acid absolutely never sleeps.
Section 3. The no-touch time clock. A fundamental rule of subsea engineering is that solid formation risk, and we're specifically talking about hydrates here, which are these rock-solid ice-like blockages, actually peaks during transient events, not during steady flow. When an unplanned shutdown hits and that warm fluid suddenly stops flowing, the entire system rapidly starts losing heat to the freezing ocean around it. The fluid inside cools directly into hydrate-forming territory, which makes this transient shutdown the single most dangerous period for the pipeline.
To fight this, we use the lumped capacitance cooldown model. This calculates our no-touch time based on fluid mass, pipeline insulation, and the surrounding seawater temperature. Think of it exactly like leaving a thermos of hot coffee out on a freezing cold counter. It doesn't get cold instantly, right? How long it actually stays warm depends entirely on the quality of that insulation. But if we miss our no-touch time window in the deep sea, we aren't just left with a bad cup of coffee. We are dealing with a multi-week, solid hydrate plug that stops absolutely everything.
And here is a critical operational rule. You can absolutely never use a fixed, generic no-touch time. It has to be recalculated for your actual real-time field conditions. Seawater temperatures shift with the seasons, the fluid composition changes over time, and hey, insulation naturally degrades as it gets older.
Assuming a generic no-touch time is a catastrophic planning error. It's the kind of mistake that turns a routine fix into a multi-million-dollar remediation nightmare. Your math always has to adapt to reality.
Section 4. Boosting declining production flow.
Now, every producing well is naturally fighting a losing battle against declining pressure. And that brings us to Fetkovich's equation. This formula evaluates the exact flow rate benefit of adding subsea boosting pumps down on the seabed to artificially lower the wellbore flowing pressure. Let's break this down with a really simple analogy. Think of extracting oil kind of like drinking a really thick milkshake through a straw. As the milkshake, which represents our reservoir pressure, thins out and drops to the bottom of the cup, it gets so much harder to pull it up. Subsea boosting acts as a powerful new straw that just keeps pulling that flow out even as the natural reservoir pressure steadily declines.
If we just rely on natural flow, we rapidly hit an economic cutoff point where it's simply no longer viable to operate. Subsea boosting fundamentally changes that curve. However, and this is vital to understand, boosting does not magically create new reserves. It doesn't. It simply accelerates and extends the economic recovery of what is already down there. It is exactly like strapping a supercharger onto an aging car engine to force out just a little more performance.
But we have to remember that timing is absolutely everything here. Subsea boosting is, at its core, an economic timing decision calculated directly against the decline curve. If you install that booster too early, you're just wasting capital. If you install it too late, you're leaving stranded reserves behind. And a word of warning, an unplanned booster failure drops that well straight back down to its natural decline curve, which puts you at risk of a massive and abrupt loss of flow.
Section 5. Surviving extreme ocean pressure.
A deep-water pipeline is not just a simple tube. It's a structure actively at war with three simultaneous forces. Imagine being intensely squeezed from the outside while simultaneously bursting from the inside. First, you have internal fluid pressure aggressively pushing outward. Second, you've got the external hydrostatic pressure of the deep ocean violently pushing inward. And third, the extreme heat of the fluid causes thermal expansion, making the pipe actually want to grow in length. But because it's firmly restrained by the seabed, all that kinetic energy converts into massive axial compression. The pipe is literally fighting itself.
So, to make sure the pipe doesn't just rupture or buckle under all these combined forces, we rely heavily on the Lemay hoop stress equations. You see, unlike a thin balloon, a high-pressure, high-temperature pipeline has incredibly thick steel walls. The Lemay equations recognize that the stress isn't uniform across that thick steel. It's actually significantly higher on the inside surface closest to the pressure source and tapers off toward the outside.
And here is a rule that catches a surprising number of people off guard. Junior engineers will often assume that a simplified, thin wall calculation is always going to be conservative and safe. But for genuinely thick-walled, high-pressure pipe, that assumption is highly unconservative and just incredibly dangerous. Thin wall math assumes uniform stress, entirely missing that massive stress spike at the inner wall. Once your wall thickness to diameter ratio crosses over into thick wall territory, using those Lemay equations becomes completely mandatory to prevent a total failure.
So, to summarize all of this, these 5 exact mathematical formulas, Salama and Tulsa for sand erosion, Deward for acid corrosion, lumped capacitance for rapid freezing, Fetkovich for reservoir energy, and Lemay for intense pressure. They are the literal difference between decades of safe, reliable energy production and catastrophic, environmentally devastating failures.
Which really leads us to a profound realization. Subsea engineering isn't just about bending huge pieces of metal and launching massive vessels. It's an exercise in immense mathematical precision. These unforgiving equations literally dictate the survival of the entire offshore industry. They are the invisible shield that protects the pristine ocean environment from the oil and simultaneously protects our vital oil from the crushing ocean environment.
We've seen exactly how we calculate our survival for today's challenges. But as global energy demands push us into even deeper, hotter, and way more hostile waters, pushing us further and further away from the safety of the shore, we really have to ask, are our current mathematical models truly ready for the extreme frontiers ahead? It's a fascinating challenge for the next generation of engineers. Thank you so much for joining me on this explainer. Keep questioning the math, and I'll see you next time.